Okay, welcome to the afternoon. Our first speaker this afternoon is Randy Katz. He holds the United Microelectronics Corp. Distinguished Professor of Computer Science. He's the Associate Chair of the EECS department, and this is the second time around for that. He holds a Berkeley PhD under Eugene Wong, and before that, a Bachelor from Cornell. He's a Fellow of the ACM, the IEEE, a member of the National Academy of Engineering, and a member of the American Academy of Arts and Sciences. He is also my co-author on RAID and ran the project that started my career. And I do think you should pull him aside and ask him to tell you about Washington and how the White House works. He's got some good stories.
Thank you, Garth. One of the things you're going to immediately notice is that my title is completely different from the program. I mean, after all, I'm a professor. I don't have to give you no stinking title. So what I'd like to talk about is smart buildings to smart cities, which is some of the research underway at Berkeley, primarily with my collaborator, David Culler. And I hope to be able to have a few stories to tell about Dave Patterson towards the end of the talk. So really, these one of the things that's very interesting, I mean, I've worked in the past on ubiquitous computing, pervasive computing, ambient computing, all of these kinds of buzzwords from 20 years ago. We're really at the point now, Dave alluded to it yesterday, of software is in everything around us, in this building, in the cars that we drive, in the airplanes that we fly in. It's remarkable how the technology has really gotten outside of the computer, or alternatively, the computer has gotten embedded in everything. And so generally this area has a really horrible sort of catchphrase associated with it, which is cyber physical systems. I hate that, but it is a sort of a current term for the idea of the embedding and computing in everything that's physically around us. One of the things that got us interested in this area in the first place was looking at the ideas in the internet architecture, the way in which we can have a protocol that allows data to be exchanged across a very heterogeneous and diverse set of communicating endpoints, and trying to think about how that model might work in the energy system, in the energy grid. So actually this work dates back about 10 years when David Culler and I started a project on smart energy called Locale. One of the things that people in the energy world know about is this how to have a bad graphic in a talk graphic, which is on one side, oops, I pressed the wrong button. On one side, all the different sources of energy in the US economy, from a little bit of hydropower all the way down to a huge amount of petroleum. That's the inputs to the system, and the outputs are where these things are used, various places in the economy, with energy wasted or sort of burned off along the way. And one of the things that jumps out at you is that two of the three major categories are buildings, residential and commercial buildings, lights, heating, cooling, what we're projecting, running the microphones, running the video cameras at the back of the room. This is consuming energy inside the built environment. And also at the bottom are how we got here this morning, which is jumping in our cars or driving or taking BART or however we got here. The transportation system also is a major chunk of where energy is used in the economy. So this idea of smart buildings and smart cities, we spend, particularly if we're computer scientists, 90% of our lives inside buildings and 10% of our lives getting between the buildings. Unless you're Dave and you're playing, soccer on Sunday. So, of course, the thing we're trying to do is all this stuff we spend 50 years, 60 years learning about computers, of course we can translate this expertise into how to build these other kinds of systems, a smart grid, a smart building, a smart city, a smart transportation system. So, of course, all these things have to have an operating system in them. So what is a traditionalist view of an operating system? In other words, a computer scientist view. Low-level, this is from Wikipedia, low-level software supporting a computer's basic function. That's a great definition. What it really does, of course, there are some critical resources in a computer system that need to be managed. Processor, memory, storage. All the talks this morning, in one way or another, we're talking about these kinds of things. provides interface to services. It provides a platform, a framework for building applications so that each application doesn't have to go forward and do everything in terms of managing the underlying resources in that computational environment. So you don't have to worry about processor scheduling if you're writing an application to present a PowerPoint slide, right? That's done by the operating system. So that service architecture, that leveraging of low-level functionality so I don't have to worry about it to build applications is a very, very important computer science concept. Now, of course, there are other aspects like communications, dealing with distributed processing, what do you do when things fail and how do you recover from them and so on. All of these are, of course, very important parts of the underlying system software that we have running on our computer systems today. Now, going forward to what would be a view from the cyber-physical world of embedding this kind of concept inside things in our physical environment, well, there are a lot of new sort of quantities to manage. It's not just about processor share, prioritization of threads, and things of that nature, although that can be part of what is going on in these environments. Certainly the management of time at multiple scales. We're processing data to control the traffic lights on minute-by-minute basis, or how we're letting people onto the freeway by the sort of flow control algorithms at the Bay Bridge, let's say. So there are certain things that are not very well. There are certain things that are operating at sort of pretty fine time scales of the order of seconds. But also these physical artifacts exist for decades, if not generations. And there's an aspect which is not unlike provisioning in computer systems, which is the planning part. How do you decide to build a new bridge? How do you, decide to tear down the Bay Bridge and build a new bridge? What sort of information processing is necessary to inform those kinds of things? And of course, our physical world exists in 3 dimensions. So understanding the 2-dimensional and 3-dimensional geographies around us and the kind of localization and regionalization of processing is very important in those worlds. And, the thing I was talking about a moment ago, energy, the sort of physical consumption of things, which are resources like energy, like water, like air, etc., are things that need to be managed in the physical world. Now, as I alluded to in the preceding slide, we want to build societal scale, city scale applications and not have to reinvent everything every time you build one of those apps. And so what are the abstractions that allow us to develop, get leverage, get speed of development as we go forward? So there are a lot of underlying functionalities in this world: sensor streams, event processing, repositories, connections to feeding into analytical engines, things that look like software-based controllers with models of behavior. So how do these become building block services in the computational environment for these kinds of applications? And so one of the also critical things about this world is when we start to talk about applications which are of a societal scale, they really have to consider that people are embedded in those systems, sorry to use that word, and that people are fundamentally irrational. They are not black boxes. You don't know how the heck they're going to behave, which is one of the remarkable things about self-driving cars. I'm not worried about the car driving itself. I'm worried about all the loonies around the car who are driving their cars, right? So how do you build systems that are kind of aware of that? How do you think of the sort of nature of interaction with people who don't always behave in a rational fashion, or will get pissed off at you when the speech recognition doesn't work quite right and start, picking you up and throwing you around if you're a piece of information technology? And of course, there's all the privacy and policy elements that are part of this as well. So it's really, to me, a fundamental definition of what is a platform is if it provides leverage. Building the second application is easier than building the first one, that there were reusable building blocks, services, interfaces, frameworks that made the construction of that second societal scale application easier. I'm going to talk about some of this as we go forward. Now, a lot of this work, of course, has been done with my colleague David Culler, and one of the problem examples from the smart buildings world is the way buildings work now is each individual subsystem, or in their world called a facility, is completely a standalone system. So the air conditioning system works by itself, the lighting system by itself, the security system by itself. And each one of these things does everything from having its world of sensors, communicating into some processing that has its own model, that is actually representative of some kind of control loop that's deciding there are too many people in this room, so it should, pump up the air conditioning, but oh, it's a very cool day because it's raining outside, so maybe not so much cooling going on, etc. So someone walks into a room and turns on the light. The HVAC system doesn't know that. Someone goes through a security door into an area of the building where there hasn't been anyone there before. The air conditioning system doesn't know that. This is the example of the kind of stovepipes that exist and the opportunity for building a leveraged platform across this that can more effectively know basically about human activity in the building, in the physical world. What are they doing? How can we understand it? How can we provide high-level services like keeping us comfortable and productive? Because we understand, the application we're building understands human activity in this physical space. So breaking through those stovepipes is a very important element of the kind of architecture we need for really building smart physical infrastructures. So another one of the how not to give a talk busy slide things is this one, showing all the different elements of energy. Don't you love it when someone says, it's all up there, but I don't want you to read it? That must be one on the 7 deadly sins of giving talks. Anyway, but it shows really the 3 major dimensions of what needs to be integrated in a so-called software-defined building or software-intensive building. The energy environment, how much does energy cost? If you care about green versus brown energy, what's the mix of available energy? How do you shape your demand for energy subject to that information? The personal environment, we walk into buildings today, we carry with us a lot of computing in our pocket. The building doesn't really make use of any of that, either to control the building or to present information about the physical environment to you. That's a major flaw. It's a little weird how the Wi-Fi works in this building, by the way, even having access to all kinds of Berkeley campus Wi-Fi, none of which seem to reach here. And the outdoor environment, understanding the current environment, the temperature, placement of the sun, how it affects the heating and cooling of the building. All of these things need to be integrated through a collection of services that get leveraged to build a building control application. And one of the things that really, in moving from the smart energy grid to a project that was looking at smart buildings, is it isn't just about the energy. Stupid. Think about it. You work for Google, and what you're going to do is save money by freezing the programmers in the winter and boiling the programmers in the summertime so that they write like -1 line of code per day. Mistake. So it's about balancing the environment and the cost of providing that environment with the productivity and level of comfort of the people in it. So in moving from smart grid to smart building, the understanding human activity and productivity and the impact of the physical environment on that and how that is actually an input to, if you would, the optimization of the system is extremely important. And that's the transition to start thinking about city-scale applications. It's about the people in the city and how we make their lives better, which is harder to quantify, but what really these applications have to be about. So our project went through several generations of these. The first generation was really building the complete instrumented environment. And you see this happening in our lives today with Fitbits and health monitors on your iPhone. And we're getting to the point where we have a highly instrumented society for good and for bad, depending upon your view of security cameras and things of that nature. Really, what we want to do is take it to the next level, which has been a major theme in our software-defined buildings project of really being able to detect and learn about human activity so that we have models of it and can exploit those models for how we do things in the building, like keep you comfortable and productive, inside the building. Don't wait till the room becomes warm before you turn the air conditioner on. Detect that there are a large number of people just walked into the room at 1:30 and adjust the cooling in advance of that. One of the things that's very important in the physical environment actually is air quality, and very few of our buildings have any way of sensing the current air quality, but probably this room doesn't. But if I knew that there were 300 or 400 people in this room, I probably should increase the airflow, whether or not I have something which is detecting how much carbon dioxide you're all consuming right now. And the third piece is the way in which we can start to use the cloud, use regionalized processing in order to learn what's going on in one building and apply that to nearby buildings, similar buildings, buildings of a similar use, even if they're in other geographic areas. So let me switch to the transportation system, since being in buildings is 90% of our time and getting between them is the 10%. Transportation, you're all aware of this. There's some really exciting things that are happening in the transportation world. There are lots of new entries in transportation. Companies like Tesla, but also Google and Apple are seriously entering into this arena, and lots of interesting partnerships that are emerging in this sector. Where probably everyone in this room has done an Uber ride, maybe within the last 24 or 48 hours. So a very different economic model that's underlying all of this. We know pretty much where all vehicles are almost all the time if we're running any mapping application, or you certainly know where all the BART trains and buses and things of that nature. Yo Taxi knows where all the taxis are. I mean, there's sort of like the amount of tracking that's going on here is enormous. And of course, there's the electrification of the vehicle fleet tying back into that energy footprint of transportation system. So lots of new partners and players. For example, Apple, which really may want to own the dashboard, but in the meantime, they have to have the egg-shaped car that none of us would be caught dead in. Some recent news just from a couple of days ago, Wall Street Journal, Ford is investing in a cloud computing company. Not a lot of money. I don't think $170 million represents that much, or $180 million represents that much. But part of this is that the old metal companies are getting into information tech. The investment is to learn about information technology. We understand we got to get more savvy about the software in the car and in the vehicle infrastructure and transportation infrastructure. It used to be the smart highway technology is there's technology embedded in the highway, and at least one thing that is becoming clear is we don't need no technology in the highway. It's all this, it's all the stuff on the edges. There's technology in the car, there's technology in your pocket, there's technology in the back end. So who really needs to dig up the highways and put technology in them? You don't have to do that anymore. So it's a really different fundamental shift that represents new opportunities and new technological challenges. And of course, here's Dave driving down the highway in his Tesla, testing the self-drive kind of thing, or at least a reasonable facsimile thereof. So that sharing economy is, of course, very interesting, and it comes up many places. Public charging stations. For some reason, the one in the garage at Berkeley seems to be used 24 hours a day. I guess free electricity is an attractor. There are certainly applications that are out there, like Uber car sharing, if you would, or on-demand rides, bicycle sharing as well. So this is something that is really coming along, and it's hard to believe for someone who grew up as a child of the 60s, and cars represented this sort of fundamental rite of passage to being a free adult was when you got your car. The idea that maybe, in another few years, who needs a car? I'll just call this sort of select something out of this circulating fleet of vehicles for providing me a ride for where I want to go on demand, rather than having this 2-ton hunk of metal parked in a garage costing a fortune even when I don't use it. And of course, the vehicle tracking I alluded to, running any of these mapping applications and so on, knows where you are, where you've been, where you're going, when you're going to get there, and so on. And apparently people are not terribly worried about this. And again, more vehicle tracking, and the way that vehicle tracking turns into fun. So if you're a Waze user, you know that they have invested in a user interface, which is a little bit more fun than traditional navigation and mapping things. Now, Waze offers a fantastic opportunity and example to tell you about because I love this application and I hate it simultaneously. I hate it because it is lacking a cognitive model of Randy's driving anxiety. So what it will sometimes do when the major roads are backed up is send Randy up a steep hillside in San Francisco to the top of the hill, where it then instructs me to make a right turn back down the hill to the bottom of the hill. At the bottom of the hill, it asks me to make a left turn up to the next hill, and so on. And of course, there are 10 cars doing exactly the same crazy route immediately in front of me. Now, this is one of those examples where I've lived in San Francisco now for over 20 years, and I have never driven on these streets ever in my entire life of living in the Bay Area for over 40 years. I have my eyes glued to my phone and not looking at all at the, sort of people crossing the street. So very, very dangerous. It would be great to have a cognitive model. So some of the challenges there: how do we turn data about trips into something actionable in terms of provisioning and managing the transportation system? What is the underlying architecture for collecting this information, concentrating it, and providing analysis across the variety of timescales to control the vehicle all the way up to the planning cycle for deciding whether you're going to build a new public transportation system or add a lane to a highway? And of course, many dimensions which are not technological but involve both economic and policy dimensions. And I think this is indicative, some of the stories I told you about the evolution of systems where humans, we find ourselves on a daily basis being embedded in technological systems that are pervasive around us. We can be the sensors in those systems in terms of collecting data about air quality, let's say, very unhealthy in Beijing, for example. But then it raises many interesting questions about who owns that data, what's the incentives to share the data, and so on. Google Glass, punch the guy in the bar because he's wearing his Google glasses kind of thing. Sometimes people don't like that. And I think a really interesting thing is not only humans as sensors, but also humans as actors in these environments, and how do we give them information so they do the right thing? How do we incentivize them, maybe economically, to behave in certain socially desirable ways, is an area where computing starts to meet cognitive processing, and it's, I think, a very exciting area for the future. So what makes a physical system smart is the sort of mantra of monitoring, modeling, and managing the environment, and some of the key technical challenges are to collect data at scale and make it actionable within the right kinds of timeframes. So there are some ways to build these systems. These are the kinds of things we're doing in our project, but I think you pretty much understand the boxology that I'm showing you. And many exciting applications to make our urban environment better as we go forward. And just to summarize and conclude, there's a lot of computer science research that can be done here, but it all flows from our ability increasingly to instrument and understand human activity. Now, I know I'm kind of running out of time, and you probably have lots of questions, but I did want to say a couple of things about Dave in this talk. So, of course, reflection on 40 years with Patterson, not 40 years of Patterson, is I think I may have been a student in the first course he taught at Berkeley. He arrived in the winter quarter of 1977. I don't know, Dave, what you taught that quarter, but in the spring, he taught a graduate course on microprogramming, and he likes to relate the story of among the people in the class was Bill Joy and Eric Schmidt and Randy Katz, and of course, Randy Katz brought down the average net worth by several orders of magnitude of the students who took that course from Dave. And of course, microprogramming, a really important concept in 2016. And of course, I've worked very closely with Dave on several projects. I went off and did my own thing for sort of order 20 years in there, and then came back to collaborate with him recently. And despite all of that, Dave actually is my #1 co-author, according to Database People. We've co-authored roughly about 8% of my papers are co-authored with Dave. One of the things I really need to reflect on, and Dave mentioned it in his talk yesterday, is what will become known, if it isn't already known, as the Patterson project model around the retreats, around the engagement with industry, the offsites. It's remarkable how few places outside of Berkeley have followed this model and how effective over literally a dozen projects that Dave was involved in and dozens of other projects at Berkeley of various people who learned at the foot of the master of how to organize these things. And it was a great opportunity to be in on the first real one of these, which was the Spur project, where we really started to develop this offsite industry invitation model and going to Tahoe and all of that. So somehow I think this will be a very historic picture and some history of computing book in the 21st century. Dave, as you can tell from his talk yesterday, family man, very important to him, his family. Just some of the stories. I sold my Volkswagen Golf convertible to Dave for his son, Dave Jr., and the purpose of selling the car, which was a convertible to Dave's son, buying it by Dave and Linda, was so that Dave Jr. would be more popular with the girls in high school. And of course, there's Mike, and I remember the sort of chaos and consternation it probably was Evans Hall at the time, when Mike was caught smoking in junior high school, and how Dave and Linda were going to, Linda had called Dave, and they were planning and plotting exactly what they were going to do when Dave got home. So one of the things I'd just like to say is, everything I've learned from Star Trek and from Dave Patterson. Everything I haven't learned from Dave Patterson, I learned from Star Trek. So Dave, of course, is a man who has boldly gone where no man has gone before. And I would just like to say, in last remark, is Dave and Linda, live long and prosper.
Questions? Do we have questions?
By the way, if you want to remember Dave, there's this great endowment fund. You can write a check and leave it with the people at the front. It's more digits before the decimal point, the better.
Yep, go.
Okay.
Hey,
Hi,
Randy.
So regarding Waze, I was afraid to use it at first because I thought giving my travel information to an independent company would be dangerous, and then Google bought them, so I figured they know everything about me already anyway. And so I've been using it ever since. I have exactly the same experience as you do, but without the hills. And but the thing is that Ben Zhao, who's a Berkeley PhD alum who at Santa Barbara now, has just gotten in the news because of finding ways to crack that and basically track people from outside of Google and just sort of use ways to tell people where they've been. So I fully agree with you about the sensitivities there, and I'm thinking this is a whole new area of research that Ben is getting into that we need a lot more help with.
Yes, I agree with you absolutely, Fred, that we now live in a world where we are pervasively tracked, whether we know it or not. We sort of know it, but we don't really think about it a whole lot, and the kind of work that Ben has done to reveal how easy it is for third parties to exploit that information, hopefully will start to make us more aware of just the danger of these things. I think also from an economic perspective, Uber has a lot of information about our trips, Google has a lot of information about our trips. From the perspective of the city of San Francisco or the Bay Area, you'd like to know about everybody's trips, or some appropriately aggregated statistics-based insight into that in order to provision, make decisions, and so on. So who owns the data? It's on my phone. I should own the data, but it sort of makes its way through the application to Uber or Google or somebody else. And I would like to actually make it available to the urban planners of the Bay Area governments, so to make a better transportation system here. So there are some policy issues that are going to come up as well, and also economic issues. What's the incentive for these companies that are collecting information about us to both protect it and to share it?
So I have a question about the Ben Zorn, Microsoft
Hi, Ben.
Research. Yeah. I have a question about the smart cities and the smart cyber-physical systems. So knowing what you know about the complexity of software and how hard it is to write correct software, and we've seen how hard it is to build these systems and make them secure, are you confident that we can go into the future with so much of our critical infrastructure relying on software?
Actually, Dave made a comment about this yesterday of, Elon Musk pushing beta software into your car on a regular basis. I think, in some sense, this agile development is some part of the story about the ability to kind of fix things fast. Obviously, we also have developed verification technology has come tremendously far over the last few decades, so that some level of safety consideration in the software that we're pushing out, they can't be pushing out something that's going to automatically brake the car in the middle of the highway. I mean, apply the brakes. So there has to be a very rigorous kind of testing, verification, and so on as part of the methodology. I think software development in 2016 has advanced dramatically in that. Will there be, a software-enabled airplane that falls out of the sky at some point? It's possible to have that sort of thing happen, but I think, the development technology has advanced very rapidly and will be continued to be, pushed in this direction because of the cyber-physical world.
Yeah, John Massey. So can you talk a little bit about interesting places that are doing really interesting things on smart cities?
Yes. So John and I were talking about Singapore at the lunch break, and I spent a fair bit of time there. It's a very, very interesting place. Not everybody might want to live there, and it isn't because it isn't a modern, well-run city. It is a sort of pervasively monitored kind of place where there is a social contract where the citizens say, for a good life, I trust the government. I'm not sure in the United States we feel the same way, for example. But they have a fully instrumented model of virtually every cubic meter of Singapore right now. They have, online digitized models of all the buildings. They can provide all of that information to emergency responders and so on. They've gone digital on everything, and they have road pricing. They have set as a societal goal to get people out of their cars in the next 10 years. So they're aggressively pursuing autonomous fleets of vehicles that will be available on demand. They are a kind of place that if a technologist says, working with the social sciences, this is good for society, and okay, Scotty, we can build it, or something like that, they will go ahead and do it. And so it's really interesting to see how fast these technologies are getting deployed at a societal scale there.
Okay. One more.
Hey, Randy.
Hi, James.
How are you? So interesting that bring up Singapore. I was giving a talk this morning at a workshop at CHI on smart cities and sponsored by Southeast Asian folks researching this. And it was clear, even as they gave this overview of Singapore, they used terms like, we'll be able to monitor you using satellites wherever you go. And it was interesting even in the language of culturally this contract of what they would allow. And I'm curious, as you think about architecting software for doing systems like this, do you think about how would we want to architect it to also pay attention to that depending on the culture? Because I said in the United States, if we use that language, people would be out with pitchforks. And then the comment was, well, they are actually monitoring you. We just don't talk about it in the same way. But how, as a software architect, might you think about it culturally?
Yeah, I mean, one of the examples that was in the press quite recently about Singapore is they identified a guy smoking too close to the entrance of a building. Here you're not allowed to smoke within 20 feet of the building. They used their remote sensing technology to not only identify that someone was doing it, but track him home and sort of write him a citation or something like that. Now, if you hate smokers, this is wonderful. But if you start thinking about what does the government know about me, maybe it's not so wonderful. So yes, I think that we have always talked about mechanism and policy in the context of operating systems. Here we're talking about societal policies, cultures, things of that nature, so that you can kind of, how much do you fuzzify the information you have, or how precise is it? Do you have mechanisms in it that under subpoena and the legal system, law enforcement can kind of tweak up the specificity of access to the data or not? We see that in the iPhone cracking situation right now. So you could imagine a technological system that had those levers in it. To say exactly how to do that, I don't have the answer for that right now. Some of the things that we do, people often often talk in the cloud environment of edge and cloud computing. There's something in between, the local or regional computing, and that could actually be not for performance reasons, but for privacy reasons. Maybe, for example, a video image of James Landay's face never leaves the building that you're currently in, is an example of how localized processing can enhance some dimensions of privacy. So, I think that there are technical parts, but also understanding the general sort of what does policy versus mechanism mean in this environment is actually a really exciting area for research.
Thank you very much.
Thank you.